6.1, we've been taking a look in this section at the set of rational numbers. We established some vocabulary last time. In particular, we had taken a look at the fact that we're talking about fractions, but they're fractions of a certain variety, right? They're fractions that have the ability to have the numerator and the denominator written as integers, okay? So not just any fractions, so pi over 3 is out the window. We're not using him, right? But we're looking at ones that have integer tops and bottoms. And we are taking a look now at some historical notes. So fractions have been used for a really long time. There's evidences of some really, some ancient societies, if you will, who've used them. Egyptians used fractions with numerators of 1. So if they had a number like 7 over 12, they would write it as 1/4 plus 1/3. That's different, right? The Greeks adopted fractions with denominators of 60 from the Babylonians, another ancient society. And we still use this sort of base number of 60 when we talk about angles. Our number system, we talk about this in one of our other elementary math classes, is actually the Hindu Arabic numeration system, developed by the Hindu and made widespread by the Arabic. And the fraction bar that we use was actually developed by the Hindu. It came into strong use, like we see it used more prevalently when we get to Europe in the 1500s, but it was developed much, much earlier than that with the Hindu. So the next thing that we're going to take a look at is going to be different models for fractions. We saw these last time. We just didn't talk about them from this point of view very strongly. Some of our views, our models, take something that's a whole and they break it apart into pieces. And some of them use a whole bunch of pieces as a collection. And then there's another one that we didn't encounter at all. So an area model is the first one I mentioned. It's where we take some sort of a whole object. So I'm going to use a rectangle because we use those frequently, but it's not the only thing we could use. So if you take a rectangle and you break it apart into pieces where some of them are shaded. So I'm going to do an example of the number 3/4 on all of my pictures. So the denominator tells you the number of pieces to break it into. So we're going to break it into 4 pieces. And then the numerator tells us how many of those pieces are sort of considered as a part of our object. So we've got 3 of them here. So this would be a shading of 3/4 of this diagram. There's nothing special about the rectangle. We do want something that can be divided nicely into pieces. So like circles work really well too. Circles and rectangles are the ones that we see most frequently. The number line model is the one that we didn't see at all last time. So again, we're still using, oh goodness, sorry about that, just a sec. Here we go. We're still using the number 3/4 for all of our models here. I'll go ahead and write it down for set model as well. But instead of actually drawing, a picture where we shade in areas, we draw a number line. So we're going to draw a line like that. We need starting location and ending location. We're starting at the number 0, we're ending at the number 1. And in very much the same way that we sort of broke the rectangle into pieces, we're going to break the number line into pieces. Breaking things in halves is pretty easy, so 3/4 is actually very nice because I can split it in half, and then I can split it in halves again. So I actually have 4 equal pieces, roughly anyway, on my diagram. And the third one over, it's this one right here, would be the number 3/4. And then we saw one example of a set model last time, and I actually mentioned it being that as well. And in a set model, we have a collection of objects. It works really nicely if the collection is actually the number that's in the denominator or a multiple of that. So like having a collection of 4 objects would work really well, but 8 would work well too, and 12 would work well too. But 5 does not work very well for this. So we want to make our, if we're creating it, we want to make our objects, that was a square. Let's try that again. Make our objects, ideally, just the numerator, the denominator of the fractions. There's four of them. And then we're going to shade in 3 of them. Oh, pity's sake. Okay. I'm not sure how to shade the object in without erasing it. Still learning, folks. Bear with me, I'm still learning. Let's try again. Okay, we're gonna go with that being good enough. 3 of them, or 4 of them now are shaded in. I shouldn't have shaded in the last one, huh? Let's just unshade that one in the middle there. There we go, that'll work. All right, 3 of the 4 of them are now shaded in. Okay, roughly. Again, it doesn't work very well when that denominator doesn't have the right number of objects. For example, if I had 5 quarters, what is 3 out of 4 of 5 quarters? It doesn't work very well. So it's easy enough to do if we're creating it, but not always easy to work with if we're receiving that denominator and those objects. Okay, fundamental law of fractions says the following. Let a over b be any fraction and n be a non-zero integer. Then a over b is equal to an over bn. You've seen this used a lot. It's how we would change denominators to match another denominator, right, when we're adding and subtracting, which is exactly what we're going to use this for in 6.2. It also has the ability to go the other direction, right? Equality works both directions. I can start from the left and go to the right, or I can start from the right and go to the left. So if I started on the right-hand side of this equation and I had an over bn, in some sense I have the ability to reduce or cancel out the like n's and go back to the a over b. So these are the fundamental law of fractions. Simplest form for fractions is what we call that when we have the numerator and the denominator and they have no common factors. Okay, another way to say that is that their greatest common divisor, that's what GCD is, the greatest common divisor is 1. We do use the denominator, again, simplest form version, not because it matters, but just in terms of the definition, that the denominator is positive. So if the whole fraction's negative, we would either put the fraction's negative in front of it or on the top if we were talking about the simplest form for the fraction. Does that sound good? Okay. So we're going to write 3 fractions equal to 7 over negative 14. So I want you to take just a couple of minutes, write down 3 fractions that are equal to this fraction. That's number 1. Number 2, I want you to share it with a neighbor. Make sure that you agree that your fractions or their fractions both achieve this goal. And then we're going to come back together and make sure that we have some good examples that maybe you didn't think of as well. Okay? So take just a minute and take a look at finding 3 fractions that are equal to 7 over negative 14. The fundamental law of fractions told us how to do that, right? Okay, there were several of the same question. Does anybody else need any clarification? Because I can say it all out loud if I need to. Okay, the fundamental law of fractions says take any non-zero number like 2. And you can use that number and you can multiply it on the top of the fraction and on the bottom of the fraction and create another fraction that has the same value as the one you started with. Okay, so if we did this with the number 2, which I did with a couple groups already, if I multiply by 2 on the top and the bottom, I will have the fraction 14 over negative 28. And that's an example of one more fraction that is the equivalent of the fraction I started with. And you can do that with any number n. It doesn't even have to be positive. It doesn't even have to be a whole number. Right? It could actually be a decimal. I'm not telling you to do that, but technically we're not telling us we can't either, right? Okay, so find yourself 2 more, besides this one, I gave you one. Find yourselves 2 more that will do that. Okay, do we got the hang of it a little bit? Okay, good. Let's give some example shout outs of some numbers that you got. Something that you have. Yes, ma'am.
Negative 28 over 56.
Excellent. Negative 28 over 56. What did you multiply by?
That would have been times 4.
That would have been times 4. And actually, it would have been times negative 4 because you moved your negative up, didn't you? Yeah, this one she actually multiplied by negative, technically. What's another one somebody has? What do you have?
21 over negative 42.
21 over negative 42. And what did you multiply by?
3.
You multiplied by 3. Very good. Okay, does anybody have another one you'd like to do? Yes?
1 over negative 7.
I'm so glad that somebody said you're really close. How about, I think it's 1 over negative 2 is what you want. Yeah? Okay. So what did we do to get 1 over negative 2?
You multiply by half.
Yeah, you multiplied actually by 1/7, or you could say we divided by 7, right? So if you multiply by 1 over 7 on top and on bottom, or equivalently divide by 7. So remember we talked we can go from this side to this side as well, right? I can move that direction, which would indicate that I'm dividing or eliminating something. If you divide by 7 on top, you get a 1, and if you divide by 7 on bottom, you get a 2. Here's something really kind of trippy though, okay? If 1 over negative 2 is an option, it also means things like 5 over negative 10 now are as well. It's hard to see that 5 over negative 10 works the same way from the original value, but it's pretty straightforward from 1 over negative 2, right? So how many of these are there? Tons. And specifically, there's infinitely many, right? We could do this all day if we wanted to. Not only that, but we have one example up here where the negative's on top. But you can put the negatives on top or on bottom, which technically would also be multiplying by a negative number instead of a positive, and create other fractions too. Okay, good job, good job. All right, let's take a look at this one. So we're going to find the simplest form. We described that the simplest form means that they have no factors in common. So we need to figure out what the factors are. In other words, how do we break numbers down? So this one has a 42 on top, and I know it says squared. We'll deal with the squared part secondarily. And we have a 35 on bottom. Let's look at 35 first. How does 35 break down?
Divide by
7 and 5. Okay, so I'm going to have a 7 and 5, and I'll put the square on the outside. 7 and 5. How could, there's more than one option, 42 break down?
7 and 6.
7 and 6. Now, some of you might have said, well, I didn't think to divide by 7 and 6. Maybe I wrote down 2 and 21. You can, but then 21 breaks down further. So that'd be okay too. This is a good breaking down of this because you can see the 7 on top and bottom matching. Shall we see that? Now we need to be a little bit careful. They are both squared. So I'm going to write that out as 7 times 6 times 7 times 6. and 7 times 5 times 7 times 5. Okay, squared means that the numbers show up twice. 7's showing up twice, 6 is showing up twice, the 5, and so on. And then what we're taking a look at from top to bottom is things that reduce, cancel out, like that n over there on that fundamental law did. What reduces? 7's on top and 7 on top and bottom both twice, right? Now, you might think, okay, well, but maybe 6 breaks down, and it does. 6 does break down into 2's and 3's. That's a true statement. But will they reduce with the 5? No, right? 2 times 3 is 6. That makes my 6, but they can't do anything to get to 5. So there's no way that the numbers on top will simplify with the numbers on bottom. So we'll multiply them back together and see what's left. I have 36 over 25. A few things to be aware of. There's nothing wrong with, this is called an improper fraction. Top is heavier than the bottom, right? There's nothing wrong with that. Perfectly fine and comfortable to leave it that way. We are going to very quickly talk about cases where we're not going to do that, but in general, there's nothing that says that this is any like worse than a mixed number or something like that. Okay, so this is an okay thing to do. Our goal was simply to have the top and the bottom have no factors in common. All right, so when are two fractions equal? Well, if we have a over b and c over d, we created some equal fractions, right? That's what you guys did together, the 7 over negative 14 one. How do we know if they're equal? Well, there's actually lots of ways. Reducing them, getting common denominators between them. We'll show some examples of those. Those are good ways to do that. But another way to do that is what you've probably heard before called cross multiplication. So if we were to set up a over b and it really is equal to c over d, what it means is that I can multiply the diagonals across one another so that I end up with d, that was supposed to say, AD on one side and BC on the other. And this is one of those statements that says if and only if. What that means is it goes in both directions. If the fractions are equal, this equality holds true. And if this equality holds true at the end, then the fractions had to have been equal. Okay, so this goes both directions. Not all statements do that. So that's a unique thing that sometimes happens and sometimes doesn't. So we're going to check, and we're going to do it 4 different ways on this next problem to see if these two fractions are equal. So one of the big things that we like to do in our elementary courses that are designed for education, or designed for elementary education, which includes early childhood and special education, of course, as well. So we like to give you lots of ways to do things. Now, it's not to try to like trip you up, I promise. But the reality is you're gonna have classrooms of students with all kinds of needs for their learning. And if you explain something one way and it doesn't make sense to a student, you need another option, right? And sometimes you need another option, like even more than just one other option. You might need 3 other options. And it's often not even, the student maybe who's struggling, it's a student who's used to seeing something from a different point of view. Or something like that, right? Like it's not always the student you would expect to have the question that will have a question. So having a toolbox of things that you can refer back to is something we sort of want to develop in your mind as you're working toward that. So we're going to take a look at 4 ways that we can do this particular problem. So it's at least 4 ways. We're going to do 4 of them. So the first one we're going to do is the theorem we just found. So this one's theorem 6.2. So theorem 6.2 says that if they're equal, and we don't know, right? It says determine. Determine means we don't know. We're checking to see, so it's sort of like a question mark here, if this works. And I would like to actually say that, do we recognize they're both negative? Okay, if they're both negative, there's no need for us to check with the negatives. They match. We can ignore the negatives for the purposes of checking because we know that's going to work out just fine. We really just need the other pieces that don't include the negative. So what this told us on theorem 6.2 is we should be able to cross multiply and check. So our first multiplication, we'll start at the top left, is 3 times 144. If you have a calculator, you want to grab it out, now would be a great time to do that. What is 3 times 144? 432. And then we're going to check the other one. What is 12 times 36? It is 432, and we know that those two are equal to one another. So since they're equal, what does it mean about the fractions? They're also equal. Okay? Now this works lovely. If I told you to multiply that by hand, you might not like me quite as much, right? Calculators are lovely. Your children might not be using calculators in the classroom, so that might not be their best number one scenario, but it works. Like it is an option one way or another. So let's look at option number 2. Let's do common denominators first. So common denominators means that we're just trying to find a denominator that they have in common, and in particular, we don't sort of pay attention to what the denominators really start out with. We really just multiply them by each other. Okay, so we take our 3 over 12, again we're ignoring negatives, and our 36 over 144. And we multiply each fraction by the other one's denominator. So the 12 gets multiplied by 144, and the 36 gets multiplied, the 144 gets multiplied by 12, including the 36. Now, because both denominators are now 12 times 144, they match. You can find out what they are if you want. In fact, we will, just because we've got calculators and we can. But that really wouldn't matter. The part that matters, because we know the denominators now match, is whether the numerators will. So let's be thorough. Let's go ahead and find it. What is 144 times 12? Does anybody have that? 144 times 12. Write it down. Ooh. I have 1728. Does that look right? Yep, 1,728. Very good. So the denominators match. Now we check the numerators. What's 3 times 144? This number will look familiar.
432.
432. And 36 times 12? 432. And look, they're equal. So the fractions were equal as well. Common denominator approach. Now, it was overkill to make that denominator that big. Okay, let's look at another one. This is the least common denominator approach. Least common denominator recognizes that it would be overkill, and it is, to actually multiply 12 times 144. And the reason it would be overkill is because I can actually multiply the 12 times something and get to 144 all by myself. What do I have to multiply 12 by to get to 144? 12. So I could just multiply this by 12. I actually think this is probably the easiest method on this particular set of numbers. So if I multiply these, I've got 36 on top and 144 on bottom. Only had one piece of multiplication in that particular method. That's pretty nice. The next one is actually reducing. So if you looked at these numbers to start with, 3 over 12 and 36 over 144, you might look at those and say, these numbers are, again, like they simplify within themselves. So if I did 3 over 12, for example, and I divided them both by 3, I get 1 over 4. That's nice. Nice, simple, clean. 36 over 144, not quite as nice and simple and clean, but you might recognize something they divide by. If you've memorized multiplication tables, you might recognize they both divide by 12. For whatever reason, we like our multiplication tables to go to 12s, okay? So if you recognize that, you can divide by 12. If you don't, you can at least recognize they divide by 2, because they're even, right? So I divide by 12, I have 3 over 12, which already looks like the other fraction, but we could keep going. And we can divide by 3 to get 1 over 4. So if we were to reduce fractions and at the end got different values, if we were to find least common denominators and at the end got different values, if we were to find common denominators and at the end get different numerators, or if we were to find this theorem 6.2 and we did the cross multiplication and got different values, then the fraction would be not equal, right? They'll all give us the same answer. They're all leading to the same place. In this one, they lead to the place that says that they're equal. So as you're taking a look at these questions and they ask you to decide if these values are equal, you can pick whichever method you want, and you might not pick the same method every time. because the fractions themselves will sometimes guide you in a direction that says, the easiest way to do this would be, right? Or maybe you just really, really, really like one of these methods. You're like, I don't care how long it takes. I'm always going to do this one because this one's the one that I like. Okay, that's fine too, but you've got some choices. All right, so not only can we take a look at whether fractions are equal, but we can also determine which one's bigger than the other one. Okay, so if they're not equal, which one's larger? This one actually tells us that if you have one fraction larger than the other one, so this one's got a over b on the left, and it is bigger than the c over d on the right. Then if you do this cross multiplication like we did in theorem 6.2, the inequality will go in the same direction. So let me actually write it out so you can see. So here's a over b and here's c over d. And if the fraction starts this way, the order does matter. You have to be a little bit more careful than you do with equalities because we need to start from the top left to bottom right. That's where we need to start. And so that gives me the AD first. So the top one is going to be the one on the left. And then the top one on the right stays on the right. So this is CB on the right. And the direction of the inequality will stay the same. Okay, and once again, this is an if and only if statement, which means that if I know this piece at the end, I can go backwards and know something about the fractions at the beginning. Now, that's great if we only have two fractions. But the example I'm about to show you actually has more than two fractions. It has three. So if you want to take them sort of two at a time and use that, you can do that. But that probably isn't really the best use of your time on this particular problem. So in much the same way as comparing fractions where we could get the denominators to match to do the comparison and say if they're equal or not, we can get the denominators to match to decide which one's the biggest as well. So taking a look at these three denominators, I have a 20, I have a 5, and I have a 10. What is a nice denominator that we can turn them all into? 20. 20 is a nice number that we can turn them all into. Some of you are saying, I see a 5 present in there. Yeah, they all have a factor of 5. So you're not wrong on that. But we want to actually turn them into the same thing. So I've got 13 over 20. This one's already done. That's nice. I have 3 over 5, and I have 7 over 10. So 3 over 5, if I want the denominator to become a 20, what do I have to multiply it by? 4. So that becomes 12 over 20, right? How about the other one, 7 over 10? If I want the denominator to become a 20, what do I multiply it by? 2. And it becomes 14 over 20. All right, it says ascending. What does ascending mean? It means increasing or going up. So think about you ascend the staircase, right? So which one is the smallest? Yeah, this one's the smallest. And which one's the largest?
14.
Yep, this one's the largest and clearly then the other one's in the middle. Now when we're giving our answer, we're still going to give the answer in the form that the numbers had to begin with. So the beginning number that we were given in the middle was not 12 over 20, right, for the smallest number. It was 3 over 5. The number in the middle stayed the same because we never changed it. It's 13 over 20. And then our largest number, 14 over 20, was given originally to us as 7 over 10. Okay, everybody good with that? All right, so this one we're trying to decide, are they equal or is one of them bigger than the other one? And I'd like to, there's lots of options. We can do the least common denominator, reduce the fractions. That's certainly an option. I've kind of shown you that a couple of times. So I don't want to go through that process again since you've got a couple of examples about all that already. But I want to give you a couple others that we haven't done as much of. The first one is the theorem 6.3 that we did in the previous, before this previous slide. So theorem 6.3 says, and we did examples of this before when we were comparing them to say, are they equal? Says that I am checking to see if they're equal or what goes between them, right? So in fact, let me just write it that way. Put a question mark there, it's 215. So that theorem says I can multiply across and I can check, right? So let's multiply top left to bottom right first. I'll write that down so that you have it in your notes in case you're looking back later. We're doing the 21 times the 215, first, and then we will do the 51 times the 430. So what is 21 times 215?
4,500.
Good. And 51 times 430? I'll help you out. 21,000. You guys are all going to bring calculators the next time, right? Yeah, absolutely. Good deal. Okay, 21,930. Those aren't the same. Which one's bigger, first one or second one?
Second one.
The second one. This one's bigger. So if I go sort of back upward, what that means is the same inequality will be between the two above. So it's telling you that 21 over 430 is less than 51 over 215. Now this one actually would work really well to get common denominators. I'm not going to do it, but it would, simply because what's 2 times 215? 430, which is the other one. Okay, so it definitely would be a good option here. I don't want to discourage you from using that. You certainly could. But I want to show you one that we haven't seen. The one I want to show you that we haven't seen, because it just asks us to put the value between them. It doesn't ask us to do it in a certain way. Is that I want us to think through this as an estimation or reasoning. Right, reasoning through this. Okay, so here's what this means. Take a look at these two numbers. We'll read them again here. 21 over 430, 50 over 215. If we're thinking about this from an estimation standpoint, the top of that first fraction, it's about 20, and it's about 400 on bottom. Agreed? I mean, that's not exact, but it's pretty close. And on the next one, I mean, look, we've got 50. It's already kind of a nice number, and I've got 200 on bottom. These would reduce really well. Not necessarily have to show the reducing, but they reduce very nicely, right? I can divide them by 10, which eliminates a 0. And I can end up getting a 2 over 40. I can divide this one by 10. And I can get a 5 over 20. We could reduce them a step further. They very quickly kind of clean up into a way that you can see that the first one's much smaller than the second one. Okay, sort of reasoning our way or estimating our way through. Let me talk to you about reasoning though. So if we reason our way through this one, it's very interesting because take a look. The first fractions numerator is smaller. Well, smaller numerators can mean smaller fractions. So the numerator is smaller. And the first fraction's denominator is bigger. Bigger denominators also mean smaller fractions. So everything about that first fraction says I'm smaller than the second one. Okay, so for this one, the numerator is smaller and the denominator is bigger, and both of these things tell you that you have a smaller fraction. So what would this look like if you were writing this down? Well, you're gonna have to tell me those kind of things, right? You might be writing me a couple sentences. That's okay. You could do the estimation. You can kind of show some of the pieces, and your estimation wouldn't necessarily have to look exactly like mine, and that'd be okay, right? We're just trying to reason through what's going on if we take this approach. Yes?
If it was like for homework, and we just like looked at it and knew, would you still want us to do another way?
You just need to describe how you knew.
Okay.
Because here's what I'm trying to avoid, and here's what we don't want. The goal is not to take your calculator and let your calculator to tell you, right? And part of that is because what you're doing, if you do that, is you're going back to what you know, prior knowledge about decimals. Decimals are not taught before fractions in school. So if you're teaching fractions to your classroom, they don't have that decimal knowledge to rely back on like you do. Y'all tracking with me on that? So we want to make sure that what we're looking at is that we're reasoning from the perspective of fractions and not from the perspective of decimals. Decimals is chapter 7. We'll get there. It's not that far off, but it's not here yet. All right. Theorem 6.4 talks about denseness. The density property for rational numbers says that if you're given any two rational numbers, there's another rational number between them, right? And if you think about this, you know this from the perspective of what happens on my screen. So I've been really trying not to zoom in and zoom out on my screen, but you understand that if I zoom in on my screen, right, You can see there's a bit of space in here between the word and the B over D, right? Like you can, that should say B. That's not what it's supposed to say. There's a typo. I'll fix that later. I didn't know it till I zoomed in. Okay, so you can see the space though, right? That's what the denseness property says. There's space in between there. If there's space in between there, which there is, there's another number in between there as well. Okay, that's what the denseness property says. So, because I think your notes, do they have it right? Do they have it wrong? Oh, good grief. Sorry, clicked on the wrong tab open. They're right in your notes? Good. Okay, well, it's just wrong on my screen. That's not what my screen shows right now. Okie dokie, there we are. Okay, so that's where we were. I'll fix that on the screen later. So there's actually a theorem that tells us how to find one such number that's in between, and it's actually really nice to use. So one way to find numbers between are to add the numbers on the ends together and divide by 2. How do I find a number halfway between 5 and 7? Well, you know it's 6, but think about it. What's 5 plus 7? 12, and what's 12 divided by 2? 6. Okay, so that's actually how you can do it. You can add the two numbers together, divide by 2. But there's an easier way when you're working with fractions that also works. It doesn't give you that same number that's in between them, but it actually gives you a number that's in between them, which is fine. What you can do is you can take those two numbers. We have a over b and c over d. You can add the numerators together, and you can add the denominators together. And the value you get will be in between the two fractions you started with. And that's a lot easier than adding fractions together and dividing by 2. So if we're taking a look at an example of this, 33 over 427 and 7 over 92, we really do not want to add these numbers together. Why? Do you know? The answer is because they don't have common denominators. If you don't have common denominators, you got to get common denominators, and I don't want to deal with 427 and find anything to do with it. That's terrible, right? But we don't have to. Our theorem that we just encountered said what I can do is I can take the 33 and the 7 and add them together. I can take the 427 and the 92 and add them together. And if I do that, I have 40 over 519. Now, that's not a particularly pretty fraction. If you wanted to verify with your calculator using decimals just for your own assurances that it really worked, you could do that, right? You could check all three of these fractions, make sure that the decimal that corresponds to them shows up between the other two. You could also take two of them and compare them with our cross multiplication, couldn't you? Make sure that this number really is bigger than 33 over 427 and really is smaller than 7 over 92. We could do that. Why must there be a number between these fractions? Well, any thoughts? Why must there? I kind of already told you. Couple thoughts. So we'll say it from a definitionally kind of perspective. Because the rational numbers are dense. Y'all know what dense is, okay, in terms of this. Think about a dense cake. What does it mean? It means heavy. It means it's really thick. And if you think about a cake that's not dense, you might think of something like an angel food cake. It's really light and fluffy and there's a lot of air in it. Right? Cotton candy, not dense. Lifesaver, dense, right? So there's always something in between, and it's not just air. It's not a vacant space like it would be in your cotton candy, okay? So because rational numbers are dense, and so let's actually define again as it is what it means to say. That is, there is always, I'm going to say space between two numbers that can be represented by another rational number. there's probably something today, maybe even if it's just this last thing about density, that you hadn't seen in a high school class or a junior high class or something before. There probably is. But one of the things that we're going to be doing that's unique to this type of courses as well is a type of questions where they look at when you're teaching, if something happens, what do you see? And the next question has that flavor, okay? So you're gonna see an example of student work. So a student has the fraction m plus n over p plus n, and they reduce it to the fraction m over p. Now there's an error there, okay? It's an error you've probably made at some point too, or maybe even have. I mean, it's not a big deal, but there is an error there. But the first question I want to know as we look at it is just what did the student do? Yeah, they canceled. And not just out the ends, they canceled out the plus n, right? They canceled out the addition part too, like all of that. Now that's not a valid operation. But why might they think to do that? Or what might lead them there?
If there was times, and you could just take it out.
Yep. If it were multiplication, this is true. Right? They're thinking about multiplication. I've had a student before who canceled out some numbers on a test, and she treated them like she was canceling out zeros, right? You know, if you have a 0 at the end, you can just cancel the 0 on the ends right there. She canceled out 9s. You can't do that, right? The only reason we can cancel out zeros is because what we're really doing is dividing by 10. But there's a reason behind what she did. It's not like it came out of nowhere. She didn't just do it for no reason. Like, she's seen something before, and this felt familiar, but it didn't apply in that circumstance. Okay, so that's what the student's doing here. So how could we help the student? Well, there's lots of options. A really good one, so I'm going to give you this, and this is a freebie for today. You guys get to work on these a little bit more as your own things later. But how could you help the students? So a really good way to help the students is a numerical example. It can be very abstract when we're looking at letters inside of math. Nod your head if you agree. You should all agree with that statement. It can be. Maybe it isn't for you, but it can be very abstract. And if you're looking at m plus n over p plus n and reducing it to m over p, and you're trying to tell the child this doesn't work, you need to be able to back it up with some evidence of why it doesn't work, and numbers are really good evidence. So let's give an example. Let's say we had, okay, that wasn't what I meant to type. Let's try again. 2 plus 3 over 5 plus 3. Small numbers. We want some small numbers. Now, let's actually just simplify this with the numerical values that we were given. So this is a 5 over an 8. Everybody good so far? Okay. Now, if we did it from the way that the student anticipated being able to do it, and we actually could cancel out the plus 3s, we'd end up with 2 over 5. Are these equal? No. What kind of justification can you give me that doesn't use decimals for why they're not equal? You got lots of them now.
The denominator and the numerator still match. And
Yeah.
You can't reduce.
They can't reduce them. That's the key. There's no way to reduce these and to turn them into the same thing. And if a student didn't like that, could you cross multiply and check it out? Sure you could. Could you get common denominators and show that the numerators don't match? Yep. Lots of options for verifying that it's not going to work. Okay. Is this what's on your paper next?
No. That's example 2.
I think I left that slide out. And I can't think for sure, but I think it might, I can't remember if it's actually because they shifted it to section 6.2, and that's why I left it out of these slides or not. Okay, let's do example 10 because I know that's in this section. We're gonna have to table this for next time a little bit anyway. Mackenzie, you're smiling over there. That's good, right? What's that mean? It means homework's not gonna be due on Monday, right? Yeah, there's not gonna be homework due on Monday because we didn't quite finish. So you guys lucked out. It also means the Success Center will be open by the time you have homework due, which is better, honestly. Let's look at this one, and we'll end with this one today, and we'll either come back and we will do the example 9 if it's supposed to be in there, or I'll tell you to mark it out. We're doing it in section 6.2 because this is one of those places where they shuffled some things and I can't remember. All right, if we take a set of numbers equivalent to 1/3 and we graph them as points on an XY axis. Okay, so here's 1/3, where the numerator is the X and the denominator is the Y. Okay, so if the numerator is X, the denominator is Y, we would be graphing this as the ordered pair 1, 3. And we want to do equivalent fractions to this. So we can take 1/3 and we can get an equivalent fraction, right? Like by multiplying by 2 on top and bottom. Okay, we did this, right? Or we could multiply by a negative on top and bottom. I'm trying to use some small numbers because it'll graph better if I use some small numbers. So this will work. So this becomes the ordered pair 2, 6, and this becomes the ordered pair -1, -3. Okay, so we're creating ordered pairs based on equivalent fractions. And if we do this and we plot them, so let's plot them now and see what happens. So we're going to have 1, 3, and 2, 6, and -1, -3. Can you tell what actually is created by these dots? What's it look like? It's a line. Now, that's pretty reasonable. It's a line. So what kind of graph do we get? This is a line. Tell me a bit about this line. Well, it goes through, we call that center point the origin. And it has one more feature. It's how steep it is. We call that slope. It has a slope of 3 because from the origin we go up 3 and over 1. That's a slope of 3. There is one problem though. There is one point on this line that should not be included in this graph. Any idea what it might be? Yeah, you're right, Bailey. It's 0, 0. This point right here should not be included in this graph. Why? You got it. Excluding 0, 0. What happens if I put 0 over 0? You do not get 1/3. That's the best we can say about that, right? We don't get 1/3. Every other point on that line, though, we would get that ratio. So we get a line, but we just get a line that excludes the origin. Okay, so either this lesson is finished, or this lesson might go back and pick up that one other question next time. Either way, we'll table this for today.